In the last lecture, we see the finite automata, and finite automata having two types, that is a with final state but no output, and second one is a with output but no final state. So we start with a DFA, that is a with final state but no output type. So this is a first one, we see DFA. After DFA we see the NFA. So today we see DFA. DFA means deterministic finite automata. So this is a DFA, deterministic finite automata. It is a mathematical model to solve the finite state machine problem or finite automata problems. So we first lecture or previous lecture we see the type 1 problem, that is a divisibility problem. So finite automata is a part we divided into in the form of a types. So we for remember or understand, we divided the whole FA topic into various types. So firstly we see divisibility types. In divisibility type we see the example based on a divisibility of a finite state machine. So decimal number is divisible by 3, 4 and any number, and then binary number is divisible by, that's problem we see in the last lecture. So today we start with type 2 problem in the deterministic finite automata, which is a that ends in. So this is the problem, that is a type of a problem. So we first take a problem, then we understand what is mean by that ends in. So question 1, define or design DFA where input is valid if it ends in 100 over alphabets 01. So this is our problem statement. So we have to design a DFA where that ends in 100, means 100, 100, not 100, 100. So over string 0 and 1. So this is the our problem. So in binary in 1001 is a input alphabets are given, 100 is the string. We have to find which numbers have ends with 100. So we in number system using binary number we can n number of a string will be the form, but we have to find that string which or string to design DFA to find that strings which is ends with 100. So we start with the problem. So here we write it, first part is a theory. In theory we write a definition of a DFA. We simply write a DFA means a deterministic finite automata, and the DFA means a deterministic finite automata. It is a mathematical model, and in DFA transition is q to q multiplied by alphabet gives q states. So epsilon transition is absent in DFA. So DFA implementation is simple because decision making in DFA is easy. So here we write a definition or theory related DFA. So we simply write deterministic finite automata is a simple mathematical model in DFA. Each state for each input symbol there can be exactly one transition. So this is a statement of a DFA. In DFA, for each state or for each input symbol there can be exactly one transition. So suppose we taking any example of a DFA in, and each state, suppose we take a Q0 state and we have an input symbol, two input symbol. Here is the input symbol 0 or 1. Suppose we transition from Q0 to Q1 is a 0 and Q0 to Q1 is 1. So for each input symbol one transition possible, not more than transition is possible. So here is a exactly one transition. This statement will be understand when we solve the actual problems of a DFA and NFA. Then we compare and get exactly mean of this problem and a difference between DFA and NFA. So remember, for at the time, remember only this statement. When we solve problems, then we understand what is the meaning of actually that statement. So implementation of a DFA is easy. DFA is a simple or easy because decision making is easy. In DFA, decision making is easy than the NFA. So in the last lecture we see the solve the problem with the help of a 5 points. So first one is a theory, second one is a logic, third one is a implementation. Third one is any formula or nothing formula. So third one is a implementation. We take a transition table, transition diagram, and lastly we see the testing part. So this is a DFA problem. So we first write theory of logic behind that problem is, here we have taken input is a given 0, 1 input alphabets, output is always yes or no. Last second states are QS is a starting state, Q0 for that the string ends with 0, Q1 state that ends with 1. We divide the one, we have to find the string that ends with 100. So this string it is divided into some subparts like 100. First we take that string that ends with 1, so 1. Then second one, that string that ends with 10. So Q2 state for string ends with 10, and Q3 is the last state for this Q3 that ends with 100. So we have to find 100 string ends with, so Q3 is our final state. So this is Q3 is the state for string ends with 100. Always remember, in the ends in problem we divide the string as a some small substrings, that is a 100 as a 1, and then 10 like some combination of the some string. Split this string and find the actual output of this problem. So here always remember, this QS is a starting state. It in every problem QS is a starting state and it is represented using arrow Q0 that ends with 0. Always take Q0 state for ends with 0 and Q1 state for ends with 1 in the that's in problem. Or suppose we have a here A, B or any, suppose input alphabets A or B, so here is a ends with A or here is a ends with B. So this is the logic behind that problem. So third one part is a implementation. In implementation, we firstly draw transition table. So this is our transition table. Here have a 3 columns because we have a 2 input string, that's why here is a only 2 columns. These are the states, it's our inputs. Input variable has a 0, 1. QS is a starting state, Q0, Q1, Q2 and Q3. We having a 5 states. So this is a transition table. Q0 is a final state. So here is a start. So Q0 string for ends with 0, Q1 for ends with 1, Q2 for ends with 1 0 and Q3 for ends with 1 0 0. So here we check QS is a state with having a 0. So here we take input 0. So ends with 0 which is string Q0. So here is a Q0. When we take on 1 is the input. 1 ends with which state? Q1 has a state for 1. It ends with 1. So next one is a ends with 0. We take from, suppose here I am written for understanding. This is for only understanding. So when we take input 0, we find string or state for which it ends with 0. So we have a Q0 state that ends with 0. So here is a 0. Here is a Q0 state. When we take 1 in this row, so 1 the state that ends with 1, that is a Q1. So here is a Q1. So here firstly input is a 0 and here input is a ends with 0. So here have a double 0. So string that ends with 0. This string ends with 0. So here is a also Q0. Here input is a 1 and the string ends with 0. So firstly take left. So it ends with 0 and input is a 1. So we have a ends with 1. So we have a state Q1. It has a 1. It ends with 1. Input take 0. So for 1 0, that string ends with or not? Yes, it obviously ends with Q2. That having a state Q2 for ends 1 0. So here is a Q2. Second one is a 1 1. The string that having a 1 1 as a ends with that string or that state we have a not taken here. So we cut the last string or first string, then we remaining 1. So here for 1 we have a state that is a Q1. So here is a Q1. Then take, here is a 1 0. This is a 1 or 0. Ends with 1 0. We take an input from 0, that is a 0. We have a 1 0 0 state. Yes, obviously we have a 1 0 0 ends in state, that is a Q3 and this is a final state. So and that 1 0 0 and then we take 1 0 and we have a upper 1. So we check, we have a string having a 1 0 1 or state having 1 0 ends. So we have a not complete string. So we split or cut that string to find the our states. So we first cut 1. So when we cut 1, then remaining is a 0 1. So we check here which having a state 0 ends with 0 1. No, here is a 1 0 but not a 0 1. So here is a no any string. So then also we cut this. So remaining is 1. So for 1 we having a state that is a ends 1, that is a q1. So here is a q1. When we take this is ends with 1 0 0 and take output is 0. So we not having a whole string 1 0 0 that ends it. But when we cut 1, that having a string ends with 0 0 0. So we having a state ends with 0. So we cut all and we having a state ends with 0. So here is a q0. When we take on 1 0 0 and here is input is a 1. So we having 1 0 0 1 ends in string is not state we have a possible. So we cut first. Then we check 0 0 1 is any state possible. No, here is a no any 0 0 1 state possible. So also we cut this. Then we check 0 1. So here 0 1 is also not possible. Then we cut 0. Then 1. So here is a 1 present that ends with 1. So we have instead q1. So this is our transition table. We understand. So we firstly take this element, then input element. We check this this is state is possible, we taken or not for this state. When we taken, then take this state, or when is not taken, then simply cut and check. And we in the DFA problem, we two state having the same states, then they combine the both state and merge the both. So we checking this problem. So we having a qs and q0 having a same output state. Also q3 have a both three having a same states, output states. But it is a one rule in DFA, only non-final and non-final. This is a non-final or starting state, that is also non-final state. Non-final and non-final state can be merged with each other, but final and not final state cannot merge with each other. Final and final state merge with each other, but non-final and non-final state merge with each other, but non-final and final not merge with each other. Suppose non-final and non-final merging is possible. Final and final state, that is a q3 is a final state. Here also merging is possible, but in non-final and final not possible. Merging is not possible. So we merge that table. So we merge these states, merge qs and q0, because both are non-final state, non-final or no final state we can merge with each other and make a transition table. So then we again draw a transition table. State input 0 1. So when we merge the two state, then we for both two state we take a one common state for both. So we take always second one which having a we merge. So we take a q0 is a both common state for this both state. So q0 q0, here is a qs and q0 are merged and both having a common output state, because we take for both one common state, that is a q0. So q0 q1, remaining is as it is q1 q2 q1, q2 q3 q1, q3 q0 and q1. So this is a concept behind that problem. And transition diagram, or we written a merging rule. In DFA we can merge two or more states where they produce same output. But they needs to be final or non-final. So then we draw the transition diagram for this table. So it's known as a conversion table. It is known as a transition table. So we draw transition diagram for this table. So we have 4 states: Q0, Q1, Q2, Q3. Here is a transition from Q0. This is a self Q0 to Q0. This is known as self transition, which is at 0. Then transition from Q0 to Q1. Q0 to Q1, here is a 1 transition. Then Q1 to Q2 transition, that is a 0. Then Q1 to Q1, that is a self transition, that is a 1. Then Q2 to Q3 is a transition, 0. Then Q2 to Q1, this is transition, then here is a 1. Then Q3 is the final step. We have a Q0 transition, it is a Q0, 0. And Q3 to last one, Q1. Q3 to Q1, this is a transition, that is a 1. So this is a transition diagram for that conversion, that is a transition table. So diagram starting state is written using arrow. So here is QS is starting state, but here when we merge that state, then Q0 is a starting state and here is a final state.